Good morning. Good morning. Can you look at everybody who's already here? That's awesome. Good morning. Good morning. Good morning. Can you hear? Wait, oh, good morning. Thank you. Okay, Alicia went. Not that
Hey,
it's
good morning.
good morning. Thank you. All right, now we're talking. All right. Excellent. All right, awesome. Excuse me, I can't hear. So good morning, Alicia. Good morning, Alejandro. Thank you for saying good morning. I forgot. Oh, good morning, Brian. Sorry. Oh, here we go. Now, here we go. This is what I'm talking about. We got to wake up here. All right. Thank you, Alicia. Thank you, Alejandro. Thank you, Brian. Or good afternoon. Jumping the gun there. Yes, good afternoon, Brian. Thank you, Alicia. Good morning, Aubrey. Awesome. Okay. Some of you have had me on Zoom before, some of you have not. I probably spend more no, it's not a fault. No fault. This is a no fault auto insurance policy. There is no fault. There is only progress. But thank you. Yes, and so okay. I think we're gonna get rolling. But yes, those of you who don't know the Zoom version of me, or those of you who do know the Zoom version of me, know that I probably spend more time on saying hello in the Zoom class than doing any physics, because I want to make sure we're all here, blah, blah, blah. So any of you who are listening right now, when you get a chance, just say good morning or put it in the chat, just so we know you're alive and we're all community, all that. Oh, also I should so I'm very glad you're making this time. I know, oh God, wait. Okay, so yeah, so I'm doing this from home. There will be a break, by the way, probably, because I know this is long and torturous on Zoom. Good morning. Thank you, Alex. Y'all, I love it. Good. Let's go. Oh, now now the enthusiasm is all right. We're gonna. And thank you. Good morning, Jonathan. John, and I got the thing 10 minutes ago. I didn't respond yet, but I got. So thank you. I totally saw that. That you responded to the blah, blah, blah. You know what I'm talking about. So you'll get those points. And I know you were the first person here, whatever. I'm just saying. Okay. Good morning, Jordan. And thank you, Jordan, again for reminding me to document that we are going to use this morning. I think you got more people coming. Okay. I do want to remind you. So I know this is going to be long. I know this is torturous. I know you're making a great effort to be here. I mean, I know it's less of a commuting effort. And maybe, maybe you're still in pajamas and all that, which is fine. Good morning, Felicia. Thank you. But I do know we all know that it's harder to get to physical class, but then once you get there, it's sort of like easier to deal with, I think, and stay awake. And it's harder to deal with this. I'm totally aware of that. We will probably have a break in the middle. I can't control when the break is because it's going to be when my dog and son force me to have one, or my son and dog. What was I going to say? Obviously, you'll do what you need to do to come in and out. Good morning. Oh, yes. So good morning, ePortfolio program. Maybe ePortfolio program, if you could tell me who, or did you just change it? Wait, oh, wow. Yeah.
Sorry, it's David. I need to change my account. I'll be right back. Sorry.
Okay, great. Thank you. But who is it though? Wait, I missed I heard what you just said, but I missed it.
It's David.
Oh, yeah, oh, great. Okay, thank you. All right, good to see you. Good to see you. Thank you. Okay. And oh wow. Oh, you're saying oh wow because of that. Okay. So we're gonna get rolling in a second. Obviously, it's gonna take some focus and concentration for all of us. And I know mostly what we're gonna do is walk through this as much as we can of the practice exam. So like it's sort of like the hardship is that we're doing it here instead of in class, but that's also like the reward for being here is I'm going to try to spell things out as much as I can for you. So the more you can tune in and stay in with me for this electronic class, hopefully you'll at least feel like your time was, worth it, because we're going to just try to prepare you as directly as we can for the exam. And yeah, and it's a double, and well, whatever. Okay. Also a reminder that a lot of those game turn options those not the game turns, the regular game thing, you might, if you get bored in the middle of class or something, or just, distracted or whatever, take a look in Google Classroom at many of those game options that you might have forgot that are all due at the end of the semester, yet not the typical weekly turns. You might have forgotten about them because some of them don't really feel like they apply to our in-person classes. It's true. Many of them were sort of written in originally for the sake of Zoom. So, but remember, like, if you show video for a little bit for some period of time during this class, then you screenshot that and you submit that later as a game thing, and you get points for showing video and things like that, or showing like for example, Alejandro right now is showing something other than a black box. He's showing a purple box with a letter in it. That makes a psychological difference on my side, and it may make a psychological difference to other students as well. Just breaking up the black boxes and just making it clear that it's him somehow. I mean, it's not the same as video, but it's better than a black box. And he can submit that later on to that portal that says game avatar. Okay. And Alec, oh, nice to see you. So now, all right. So thank you. And I will try not, and if people show video, I'll try not to call attention. I'll try. It's hard not to, but I really appreciate, oh, all right. See, now we're, okay. See, doesn't that help? Doesn't everybody feel so much more awake now? And those guys, and I want to thank those guys for showing video. Wait, here comes Kapana also. I will get rolling in a second, but it does make, I'm not forcing anybody, but you get points for doing it. And to make it clear to Alex and Alejandro and anybody else who might have the strength of character at some point to show a little video, I want to make it clear to them right now that I know their video is going to go off at a certain moment. It's going to have to, like, even if they just have to go to the bathroom, whatever. I understand that. And that's totally fine. The one real stupid, I shouldn't say stupid. The one mistake we all make is thinking that the minute we turn on video, then everybody else is going to see when we turn it off. And then that's going to be like signal something and be even worse. It's not. I understand their video is going to go off at some point. It doesn't, it's still a net benefit that it went on for any amount of time. Okay. And that's the same thing with avatars or talking. I want to get this out of the way because I haven't had all of you on Zoom. There's tons of ways that you can participate from moment to moment during this class today, all of which you can submit for points in the portals, and they're all worth it, including the biggest thing of all. I'm going to try as much as I can, to stop and ask you questions where you can put things in the chat. You can totally use the private chat. In fact, I highly encourage it. I used to not, but I do now. When I ask little questions like, so what's the cosine of 0 or something, please feel free to put answers in the direct chat. I will not use your name, but I will talk about whatever you put there or put questions. The more you use the direct chat, you can get tons of points, and it really helps us all stay awake. It'll help you more than anybody. Anytime you type anything in or say anything or show video, I promise it helps you get more out of the material. So just bear in mind that there's all these portals for all these ways you could participate, and never think that if you suddenly remind me that you exist and then you fade out, that I'm going to remember the fade out. I'm not. I'm just going to remember the moment that you existed and then it helped the class. All right. But especially since we're going to be talking about this exam. Oh, great. Thank you. Yes. Thank you, David. Oh yeah. I remember this now from that's right. This 11/18. Right. Scorpio. Okay. So yeah, and again, and I apologize also, just like with regular class, if I occasionally do my ADHD, if I say weird things that are not exactly like physics, part of it is just to try to keep us all awake and enthusiastic. Okay. So at any time, at all times, put things in the chat. Some of you already have it from real class. You can put things in the chat like please slow down or please speed up or whatever. And it's all understood that this is rough. Okay. But again, thank you, Alex and Alejandro, for being such human beings. Oh, and thank you, Tobias. See, whoa. Okay, that's creepy. And I'll try to restrict my comments. And thank you, Kalpana. Again, it just shows, just somehow it just breaks things up. I appreciate it, Kalpana. I appreciate it, Tobias. I appreciate it, Alejandro and Alex. Okay, I'm gonna get rolling now. What I'm gonna do, I'm going to try to walk through as much of this practice exam as I can. I'm hoping you maybe looked at it and maybe have questions to redirect me or to pace me. But for now, especially as we're waking up, I'm just going to start going through it. I'm going to go through it in order that I think makes sense. It's not necessarily cover to cover. All right, so hold. All right, let me just pull it up. Hold on. Okay, so bear with me for a second. I'm going to pull it up. Also, I'm going to be, changing the view on the screen from. Oh, someone just showed me. So, okay, wait. For example, sorry. It's coming. It's coming. Oh, yes. Thank you, Jocelyn. All right. Good morning, Jocelyn. Also, I owe Jocelyn something, but that's a subject for another time. All right. But I haven't forgot. Okay, so here comes the board. You can see the board. Okay. And this happens. Yes, this happens. Hold on. Sorry. Hold on. Okay. Okay. Now I just have to pull up what I'm going to do. Hold on. We're juggling more than one screen at once. I'm going to. Okay, here we go. All right, I'm going to start, believe it or not, I'm going to start with problem 2 of the practice exam. Problem 2, not problem 1, because problem 1, as far as I'm concerned, we did a bunch of it already, the main parts last week in class, right? There's still some questions at the end. If we have time, you can ask me about them or I can go back to them. I mean, some parts, but I think to really get rolling, it'd be better for me to start with problem 2 on the practice exam. So here we go. And right now, I'm trying. Well, yeah, I'm going to try right now to hold on. I'm trying, at least right now. Oh, I owe Jocelyn 2 things actually, or I know her thing. All right, sorry, I'm talking out loud. But yes, this reminds me. I will post something to help again with the 5-step problem method. I've been very behind, but I do expect the 5-step problem solving method on exams, right? Do you literally have to write step 1, step 2, step 3? No, you don't literally have to literally write step 1, step 2, but honestly, I'd advise it. I mean, I think it only helps you and helps me if you do that. I wouldn't take off points if you didn't literally write step 1 or step 2, because that's not literally physics. But so anyway, right now I'm going to try, at least at the beginning of this, like I did last week, to try to walk you through this and give you a sample solution with the 5-step method as though I were a student. I will try, at least right now. So hold on one second. So that's what I'm doing right here. This is problem 2 for anybody who just tuned in. This is problem 2 of the practice exam. And please put in the chat if you don't see the practice exam in your Google Classroom, please let me know. I believe it's there. I believe I confirmed. And I do want to thank you. Those of you students who reminded me by text to post it definitely made a difference, definitely appreciated. Okay. Sorry, as you can see, I'm also warming up here. Okay. Okay. And I'm just scrolling. Again, I also apologize. Like I'm looking at 3 screens at once. I'm trying to draw this for you, but I'm looking at, so I can't see for the moment. I cannot actually see your faces or what's in the chat. If there's anything, I will look in 1 second. I just want to see. Okay. Okay. Um, oh, I see. Okay, okay, okay. Okay. Um, um, okay. There's stuff in the chat already. I apologize. All right, I'm looking now. 1 second. Okay, wait. Okay, the chat is very funny. Oh my God. Okay. Wow. All right. And yes, I will admit right now, if anybody's wondering, all this craziness that's in the chat, at least for right now, yes, it helps us all more than it hurts. And yes, this counts as participation. I mean, at least until I get rolling, anything we can do to keep us all awake. Yes. So, okay. Sorry. Yeah. Okay. That is funny. All right. All right. Oh, and there's more people entering. Okay. And I see things have happened. Okay. All right. So again, and maybe someone, as long as you're using the chat, maybe someone put in the chat privately or publicly, can you confirm that, or no, how about just this? Please put up your electronic hands if you have the practice exam, not your answers, but just if you have the questions like in front of you, if you see the practice exam. Thank you, Felicia. Thank you, Aubrey. Awesome. Thank you, Brian. Thank you, Jonathan. Thank you, Brian. Thank you, Jordan. Thank you, Kalpana. Thank you, Jocelyn. Thank you, Alejandro. Thank you, Alex. All right, awesome. And by the way, and I'm thinking, and not to be weird, but John, it's John. Tell me privately or publicly, Jonathan. I've been thinking I'm supposed to say John, but the box says Jonathan. I want to make sure which you prefer, John or Jonathan. Just you can tell me in the chat. But all right, great. Oh, and there's Felicia. Okay, now. Oh, and there's Alicia. Oh, we are rocking. She's at John Jay. Oh my God. But I know she got. Oh, so she. Okay, I'm not looking. I am looking. I'm totally looking. Okay. All right. So we're doing problem 2. You see how long it's. God, can you imagine? Do not go inside my mind without a flashlight, 3 therapists, and a search party. Seriously. Okay. All right. So we're doing problem 2 in the practice midterm. I'm trying to do the 5-step method. So, and also I should make clear, you might have noticed that the instructions. No. I'm going to make 2 more things clear. One, remember, if I give you solutions, like I'm about to solve this problem, right? I'm not going to necessarily finish everything in the practice. I'm going to finish as much as I can. Anything where I give you the explicit solution, then when you get your actual exam, of course, I'm going to tweak things slightly, like change numbers or this or that. There will be slight adjustments to make sure you're still thinking and not just copying from today, right? But anything that I don't give you the solution at all, just remember this too. If we don't get to something in the going over this, then the one benefit of that is you'll know pretty much it's going to appear verbatim in your real thing. So you consider it like a research project. Like if I don't go over something, then what that means is now at least you have the super advanced warning that's what the question is exactly. Okay. Oh, and also, David, are you still having hand up from before, or is that a question? Maybe that's it. Okay. Okay. All right. So the other thing is, you might have noticed in the practice exam, I think at the beginning, it said something like the instructions solve all of these problems. And yes, you might have noticed the way it was worded. That meant for this practice, we got to try to, we need to, all of these we're responsible for. Any of this stuff could appear on the real thing. But it's likely that on the real thing, you'll have a choice here or there. That's not a total promise, but it's very likely that if you get the exam and it looks very long, it's because I'm giving you a choice between one problem or another. But often it's like, you must do this and you must do this, but then you can choose between this and this. Whatever it says, you've got to follow it explicitly, and you cannot do extra for extra credit, just to warn you. Like, I don't have time to grade it. I mean, it comes down to that. So they just like do what it says. Okay, so here we are in this one. And thank you. Okay, thank you, John and Jonathan. Awesome, I appreciate that. And that was points for participation and for closing the conversational loop. Totally submit that for points. Thank you. All right, awesome. Okay, so here's this problem. I've now done, so this is the problem. I've now done step one, right? I've drawn a diagram, and I've given the facts. Notice this, just as a piece of advice for the exam and for physics. Even before the problem started, I drew my own diagram. I know, and you know, if you're looking at the question, part one of the question asks for a diagram, but it asks for a free body diagram. That's a very specific type of diagram, which of course I will do in a moment. That's a particular type of diagram from Physics 203 that's necessary for getting the forces delineated. That's a question. Before you answer any questions, step one of solving physics problems is drawing a picture of the situation. This is a picture of the situation. This is not a free body diagram, all right? And it's really necessary. So notice now we've had three things. We've had physics problems where they give you a diagram right away, and I say still start by making your own version of that very same diagram. We've had physics problem, that was homework 1. In homework 2, we had a math question where no diagram was presented at all, and I still say start with a diagram, and meaning like a cosine graph in that case. And now, example 3 on this exam, it starts with a question, and it right away asks you for a diagram. But even before that, I'm saying that is not what we mean by a starting picture. So please bear that in mind. This picture that I just drew is the facts of the situation. I'm not solving anything. I'm not doing any vectors. I'm not analyzing anything. I'm just presenting the facts of the situation. And notice the way I'm presenting the facts of the situation, the actual picture, the purpose of it is that every variable or constant that's going to be used in my math is a label in this picture. Like L is there in the picture, M is there in the picture, theta naught is there in the picture. So that the purpose is so that when I start using those variables or constants in my math, we all know what I'm talking about. This picture is there to define the terms of the problem. It's there to make it, I'm going to stop in a second, I promise, but it's there to make it so that even that someone could follow this solution even if they didn't have the exam in front of them, or someone could grade the solution even if they didn't have the exam in front of them, and therefore maybe ever get you the grading back in any reasonable amount of time. Like, honestly, right? So I've labeled the picture with general letters like L and M and blah, blah, blah. And then under that, I'm saying, oh, and in this case, by the way, L happens to be 5 meters. Oh, in this case, M happens to be 3 kilograms, etc. This is why we call it diagram and fact pattern. It's a diagram, and then it's the particular fact. Okay, so that's my starter thing. It's not a free body diagram. It's a picture. Last thing, in terms of this particular problem, you might notice that the intro of the problem says that this pendulum is like deep in the center of the earth. It's kind of or something like that. That's like a weird thing to say, and I don't want to make too big of a deal of it. But the reason it's saying that actually is it's actually trying to discourage you from going about figuring. Eventually in this problem, it's going to ask you to solve for the angular frequency, like almost right away, and that's what I'm about to do. Well, maybe when I get there, I'll say more details. But the reason this thing says that it's somewhere deep below the surface of the earth is actually, it's trying to say, you don't know for a fact here that G equals 9.8 meters per second squared. That may sound like an obnoxious thing to say or weird, but it's saying that. It's saying it's deep below the surface of the earth to make sure that you solve this problem the right way, not the wrong way. It's actually a helpful hint. I guess I'll say more details about that when I get to that part, but that's why it says, I've written here in the picture, like, note, G equals question mark, question mark. I'm not saying we're going to solve for G. We're not, but I'm saying we're not going to assume that we know that G is 9.8. All right, you'll see what I mean in a second. So, all right, anyway, that's my picture. I'm taking way too long. Surprise, surprise. So that's my step one. So then step two, is what is the question? And of course, I don't know because I have to switch my screen. Bear with me for, okay. Oh, okay. Yeah. All right. So now, what is the question? The question is FBD. Okay. It's okay. So here we go. All right. Now this is a physics 203 thing. We need it to get some physics 204 information. So I don't want to over dwell on this, but so I'm now solving this, right? Okay. Okay. I dragged this out a little bit, but all right. So this is asking for a free body diagram. I'm not saying you have to, I'm just trying to do the step method as explicitly as I can. And also I'm just trying to remind you, since it's been a while since physics 203. Well, in fact, well, yeah. All right. It's asking for a free body diagram. The truth is, I just want to remind you, there's really two types of free body diagrams. There's a pure free body diagram. There is the actual free body diagram. And that's what I assume this problem is asking for, since it didn't specify any further. And it's not asking me to do any computations yet. It's just asking for a diagram. So I'm going to draw the pure free body diagram, which means I stand in the reference frame of the lab. I look at the situation, right? In other words, I'm in the reference frame of the lab. I'm looking at the situation. And I'm delineating every single force that acts on the point mass being the pendulum bob here, the M, right? So for every force that's acting on it, I draw an arrow whose tail is at the point mass, I'm just reminding you, and whose tip points in the direction of the actual force, right? And the rule of thumb from physics 203, the rule from physics 203 is you always draw a vertical downward pointing force indicating the weight or the pull of gravity on the object, and we call that mg, mass times acceleration, mg. That's always pointing down. And then in addition to that, you draw any and every thing that's touching the object. So there's gravity, and then we're just looking at everything that's touching this object. The only thing that's touching the object is the string. The string is pulling up and to the left, according to my picture. So we say the force of tension exerted by the string is pulling up and to the left. So this is my pure free body diagram. Now there's actually a reason that I need it. So I want to say a tiny bit more about it. I mean, but that, that's my answer. That's my pure free body diagram. But notice a couple of things. Number one, there's nothing in it besides the forces acting on the object. There is nothing in it. There's no length. The length of the string is not indicated. Velocity is not indicated. Acceleration is not indicated. Nothing is indicated besides the forces. There's other important information in this problem, and that's why we put it in the opening diagram. But that other information is not part of a free body diagram. I'm emphasizing this because honestly, semester after semester, people try to combine these two pictures into one, or they for whatever reason, they often give me a lot of extra information in the free body diagram, and that's actually very confusing and ultimately leads to mistakes. The free body diagram, particularly the pure free body diagram, should only be the forces. So we have this picture here. That's before the problem started. Then we have the pure free body diagram here. Okay. And there goes my board. Okay. And notice, like it's the string that is pulling the object. But as far as forces, sorry. Oh, great question. Thank you. There's a question in the direct chat. Okay, great question in the direct chat. I'm going to keep my promise and not mention the person's name because it's in the direct chat. But I'm going to say the question is a great one. It says, does it necessarily have to be to the left or can be up and to the right? That's in other words, the direction of my tension. That's a great question. I meant to say something about that. There is an answer to that question. The deal is this. This diagram that I just drew for the pure free body diagram could be the other way. Sure, it could, but it could be the only way only if my original diagram is the other way. This is also part of the purpose of my original picture. This is very important, honestly. I'm glad someone just asked this. I'm saying I first drew this picture to show you what I'm visualizing as the string of our pendulum. Right. And as the arbitrary photograph moment that I'm picturing a moment where the mass, I'm doing this wrong with my hand, but where the mass is here and the nail that's holding the fulcrum is up here. Once I draw this first picture is up to me, but once I draw it, then the free body diagram has to be consistent with this. This almost is showing me the orientation in my mind, showing you the orientation in my mind. So this picture could have been flipped. That would be fine. And then the next picture would be flipped accordingly. But I needed to be clear that the tension in this string goes along the string. So, and the person who just asked in that direct chat, if they want to acknowledge, exact. Oh, they just got so many points for closing the conversation, lifting it. Yes. The person in direct chat just wrote got it. So based on initial image is the reference. Yeah, the initial image is the reference. And again, that's part of the purpose of your initial image. It is to establish reference frame and coordinate system, perspective, all that. Absolutely great stuff. And again, I just want to say to everybody, I totally respect that. I love the stuff in the chat. If you have the slightest unsureness of how I'm going to feel or the class is going to feel, use the direct chat like this person's doing. And I'm going to do exactly what I just did. I'm going to use the content of what you're saying. I'm not going to use your name. But don't get me wrong also, if you feel like going public, all the better. I really should make separate portals for that. There's this person, what they just put in the direct chat, I want to say it's an example to everybody of what I do want to see. Even if they were making a mistake or they were confused, all the better. If for their own dignity, they want to stay in private, that's fine. But I also just want to make clear, I don't think there's any shame in quite the reverse. But anyway, so, and if a person wants to go, if one of you wants to go in private, tentatively first, and then see how I react, and then follow up in public, also totally fine. Okay, so I'm not going to mention this person's name unless they want until they want me to, but I'm going to say that that was a perfect question that was in the direct chat. Okay. And it was a perfect follow-up. All right. So that's my pure free body diagram. Oh, and last thing about it. This is a little bit subtle too, but you know, pure free body diagram, the vectors are supposed to show direction. That's possibly the real important thing, but they're also supposed to show comparative, qualitative, intuitive magnitude. Like we're not doing calculations in the diagram, they're not numbers, but basically what I'm saying is if you know for a fact that two arrows are equal in magnitude, if you really feel you know that for a fact and you're going to use it in an important way in the problem, then make them clearly equal in magnitude. And you can even draw a little line on each one that shows they're equal. But if you don't know that they're equal, make it clear that they're not equal, if that makes sense. Like I'm trying to make it clear here that I don't think there's any reason to assume that the tension and the weight of the object are balanced. Like they're not. In fact, I believe the tension is greater than the weight of the object. Otherwise, I don't think the thing is going to stay in a circle. But even if you're not even if you made the weight greater than the tension, I don't think I would take off points for that. But if you like went out on a limb and asserted that they were equal when they're not, that can get dangerous. So try to be explicit about comparative magnitudes. All right, anyway, I'm going to move on. Okay. I'm going to move on. We're doing what, and I will try to speed up as always. I know I always start really slow. I'm just getting I keep switching screens. Hold on. Oh, there we go. Okay. Oh, question. Yes, I'm sorry. Yes.
Could you speak a little bit about like the GDP, like when we should like express, because I know like GDP usually like in most situations you list like relevant equations or facts, like in this instance you explained what a free body diagram is. Can you like talk a little bit like when we should like explanatory about like what we're doing with that? Because
Yeah, no, that's a really good question. Oh, and thank you, Tobias, for showing video. That's awesome. Wow, that's a crazy. Okay, sorry. Yes, that's a very fair question. And I will admit, it is the GDP is a little bit dicey when they're literally asking for a diagram. There isn't as much to say about the GDP. I would say if there's anything else that you might add to the GDP here, it's like the things that, like, you might say, for example, hold on. Wait, that's really good. Okay, I want to address, I'm so glad you guys are participating like this. I want to address in a moment what Brian just put in the chat, but still on Alex's thing. If you were to add anything else to the GDP, maybe you want to say like the tension, like the T stands for tension, the tension in a string is directed along a string. That's, in other words, that's where I got that arrow from. I don't think you need to say much more in the GDP for this. It is a little bit tricky because it is just asking for a picture. But as long as you're asking, and I will go back to the chat in a second, as long as you're asking, we're going to see down by the time we get to part 5 of this problem, it starts asking you to really use the diagram. By the time we get to 5, this diagram is only going to be serving its purpose if we start dividing the forces into components. So what I really want to say is, I think this is sufficient for the GDP here. Because right here, all it's asking is the diagram. But just to warn you or just tell you like why this is even happening in the problem, I think at some point we're going to have to break these vectors into components. And you can choose to do that now, or we can choose to do it when it becomes necessary in part 5. I mean, and that's what I'm going to do. And when I divide them into components, I think there's going to be a little bit more GDP to write. But bottom line, you're right. Normally speaking, a GDP is some kind of equation or definition or principle that could be written probably in an equation form. Here, I don't really think there's any equations to write because the equations are going to come from this diagram. And it is a little bit unusual that the step of a problem is literally explicitly asking for the diagram. So I think this is all to say about the GDP here, but you're right. Generally, the test of a GDP is if you've used a triple equal sign somewhere in a GDP, you've definitely done it a good thing. 90% of the time, the GDP will have some kind of triple equal sign statement, but just here, I don't think there is because they're asking for a picture, but that's a good question. And you could tell me in the chat if I followed up or not. Now, yeah, and on Brian's thing in the chat, okay, I'm really glad I put this 2 things. On the one hand, he's making me realize another thing. When he says, I'm going to go backwards of what Brian just said, oh, cool. Thank you, Alex. Okay, cool. When he said anything in general, that's a really good point when he wrote anything in general, because I also want to say to Alex and to everybody, with a GDP, the good news is you're not taking a risk by saying more and more and more and more. The thing about a GDP, and this is actually the interesting thing about a GDP, the more you get used to it, is GDP is supposed to be about things that are true even before the problem begins, right? Like I may not have said perfect things here, but I'm saying like tension from a string is directed along the string. Okay, that is a true statement. I know that's a true statement. The only thing that might be a doubt in my mind is that really what the professor is looking for right here? Or is that really that helpful to me in this problem? Or am I really, really going to use that or blah, blah, blah? But the thing about a GDP is none of that matters. If you write something that is true in the GDP, if it is true in general physics, then it's true and you'll get full credit. You will not lose points if what you're saying is true in the GDP, even if you end up not you. So if you wrote down, for example, so like where Brian just said anything in general, honestly, I could write F equals MA right here in the GDP because honestly, that's always somehow on the topic of a free body diagram. I could write it down now, and even if I'm not using it yet, I promise you, you would not lose. You could write it down and you would not lose points. You would gain points. Anything that is true is good news for a GDP. And then you can pick and choose from your truths how exactly you're going to use them in step 4. Step 4 is when you start turning the crank and applying general truths to particular methods. I'm going to say this. This is just such a good question. And honestly, I'm glad Alex, it's not the first time Alex has pressed me on the GDP. I mean, sometimes it's like outside of class, and I'm glad he does, because the GDP, honestly, is the thing. It really does make difference once you get used to it. It's okay. That's funny, Brian. Okay, I'm going to take the risk of saying this one more time. The whole idea of the step 3, step 4 sequence. I'm saying this again. I know you all know from 7th grade. Believe me, I know that like when you first started doing math in 7th grade, whatever grade, of course they all taught you like write down what you know and then write down all the facts and then write down what you're solving for or something. Like I know it's not news to any of you that you should first write down what you know and then start working it. But here's what I'm saying is the news. What I'm saying is the news is that if you're not explicit about step 3 and then step 4, what science students, including me, tend to do, especially when they're nervous, what we all tend to do is write down facts from the problem. We tend to write down first things that we think are relevant. We tend to first stress about what we think the professor or the question or the world is looking for. We tend to do that. So like we tend to write down the facts of the problem, things that we think are relevant, and then we try to make them true. I do that all the time when I'm not really being vigilant. And it's not conscious. It's a response to nervousness. What I'm saying, the grand trick of getting out of that trap is flip the order and try to write down things that are just true first, and then try to make them relevant. That takes discipline. It's right that Alex keeps sort of pressing me on this distinction, because it is a subtle distinction. What I'm really saying to everybody is the model for solving a physics problem is this: all people are mortal. Michelle Obama is a person. Therefore, Michelle Obama is mortal. And I'm just using her as an example, obviously. I mean, I'm not like wishing her death. I'm just using her as an example. But notice the model of that thinking. All people are mortal. Michelle Obama is a person. Therefore, Michelle Obama is mortal. That's a classic syllogism. That is the classic model of deductive reasoning. You start with a general truth that's indisputable. People are mortal. Then you apply it to the particular situation. Oh, let's talk about Michelle Obama for a minute. Oh, she's a person. Oh, then Michelle Obama is mortal, right? I'm serious. So what we're trying to do here is always start with an indisputable general truth and then shrink it down to the level of the problem. So you start with truth and make it relevant. Don't start with relevance and then try to make it true. So, okay, so I'm off but that's so a GDP is supposed to be, so I'm saying you can err on the side, even if there's things that are in Alex's or Brian's mind right now that I didn't say that they might have said for the GDP. Good, as long as they're true, they cannot hurt. Then in step 4, you think about how to apply those truths. Last thing though, and then I'm gonna look at the chat. I see things are thinking, I know I'm going crazy again, but just also with all due respect also to Brian, and thank you for going public with this. And what I'm about to say is a slight correction, so he can also submit this for points for being wrong. Like with the 9, that G is 9.8, that would generally be a general truth, but it's actually not in this problem. Like, be careful, because this problem already said at the beginning that we're like deep under the surface of there. So we don't actually know that G is 9.8 in this problem. So that I would be careful about. I mean, but we do know that weight is m times g. Sure, that you could put down. But okay, now, okay, cool. Okay, I'm looking at the chat. Okay, funny. Okay, cool. All right, thank you, Huxley. Brian's funny but helpful. Totally, all this is very helpful and funny. Felicia gets points. Okay, sorry. Okay, she doesn't. That's funny. I'm sorry, I will not be fixing. Okay, that's funny. All right, I will miss you guys very much when I die, because I'm very mortal. Okay, so that's that. And I promise I just used Michelle. Could have used anybody example. Okay. Okay, so now we're going to go on finally to. So question 2, I believe, asked, what is omega? Right, I believe. Okay. Sorry, I keep. What is? Yeah. What is the angular frequency of the oscillator? All right, now to get. Oh, okay. Actually. So step 1, diagram and fact pattern. I'm going to say for a diagram, see above. So you can do that, right? I mean, I'm going to say for diagram, see above. And often you could say for, until further notice. Right, so now I'm saying I'm not going to draw the diagram each time, and I'm not even going to make this note each time. I'm saying from here on in, I'm acknowledging there's the same diagram, blah, blah, blah. You get the point. And then it says, but then what's step 2? What is the question? So the question is, what is omega? Now, step 3. Now we're step 3, GDP. Now here's where my little technicality on the Brian thing and on the G. Sidebar, I know many of you have now come to understand, either from lab or from the internet, or, if you've really been paying attention to class, you may understand that one way of getting omega on a pendulum is the square root of G over L. I'll talk more about that, but I'm not going to say that here. That's not my GDP here because, well, first of all, it's not a GDP. So that's what I want to blow past. The way to solve this problem now is not to think that omega equals square root of G over L. I'll get to that. We're going to prove it at the end. We're going to show how you derive that, but that's not a first principle. That's not a definition. Again, this is back to Alex's thing. Square root of G over L might be an equation. It might. I mean, it is. But it's a double equal sign. It's not a triple equal sign. We arrived at, and if you don't even know what I'm talking about, that's fine too, because I don't want you to use it here. But square root of G over L, or same thing with like square root of K over M for a spring, that's something we figure out. It's not in the dictionary. It's not a law. It's something we figure out. And here, it would really get us into trouble, either to call that a GDP or to use it, because this is asking, this question, I should even say, this is asking 3 sig figs. This question is asking omega to 3 sig figs. Now, why is that significant? Why? That's his way of saying, I want a number here. Okay, I'm not really telling you that we're going to get all bent out of shape over significant figures. It's not a chemistry exam, and it's not the lab. But when I say in an exam to 3 significant figures, that's really my way of saying I'm looking for a number, because I'm not always looking for a number. That's my way of saying I'm looking for a number. And it's my way of saying it's probably not going to be a pretty number. It's almost my way of helping you and saying you're going to get some kind of crazy number and you're going to chop off the digits, and that's fine. So roughly chop them off to 3 is what I'm saying. Okay, but that's a warning that I want a number here. So how am I going to get a number here? Yeah, how am I going to get a number here? The GDP is that this, now I almost, oh wait, it's 8:50, I'm looking at the time. This is where we're getting to the meat of the exam now. Like, this is a real question. Question 2, what is the angular frequency of this? I'm not saying it's hard, but you have to have been in this class to know how to do this. Like, it does take a moment of thought. So I'm almost tempted to see if anybody in the chat wants to give me a hint. Well, here's a hint to you, and then I'm going to see if anybody can tell me in the chat. The way to get this, the GDP we're looking for here, is the same GDP that we used to solve homework 3 last week in class. Like, this is totally like the first question of homework 3. And if you, even though that was about temperature, and this is suddenly about a pendulum, and I'm even going to warn you further, the idea is the same, that if you walk in and if we didn't do this practice and this was an in-class exam and you walked into this exam today and you saw this problem, if you open this problem, you might well have the reaction, wait, what? Pendulum? Like, if you were like me and I opened this problem, I would think 2 things. I would think, pendulum? We didn't do any homework problem on pendulum. He hasn't said anything mathematical about pendulums in the middle of the class. And then I'd think, oh crap, we did this in lab. And then I would think, are you kidding me? He's just out of nowhere asking me about something we did in lab, even though like he barely warned us. And like, I mean, and then I would be like, I know technically I'm responsible for the lab and blah, blah, blah. And yes, I remember this from lab, but Jesus, I wasn't expecting a lab thing in the middle of this exam. What a jerk. Like, I would get all my feathers ruffled if I saw this on an exam out of nowhere, right? But and I understand that if you're thinking that, I mean, hopefully you're not, because here we are practicing it together. But if your first reaction is to think, wait, this is a freaking lab thing, like I don't remember ever practicing this, I get it. But it's just like homework 3. The point is that this is an exam, a physical example of the math that we have been saying is true across the universe time and time again. So you want to get used to the fact that whether we're talking about D for temperature or X for a mass on a spring, or in this case, theta for a bob on a string. What we're saying is there's a general physical principle here that applies to all these seemingly different situations. And why we've been spending so long on this one freaking thing is because it's such a broad, big thing, i.e. oscillation, harmonic oscillation. So I'm going to pause for a second and say the way you get angular frequency here, the way you get it, the GDP you're looking for is the same GDP we used on homework 3 or on the other problem last week. Okay, so I'm going to look in the, I'm switching screens again, so maybe it's in the chat right here. Let me see. Yeah. That's awesome. So there's one person in the direct chat. I'm not going to use his or her name. Yeah. Oh, she or he just busted a move big time. Yeah. Oh, that's awesome. Person whose name shall remain nameless. I'm looking carefully because he or she just like put severe math, specific math GDP into the direct chat. And I'm like, it deserves, and it's right. Wait, I'm even going to press my luck. Okay. Oh, yeah, you're totally right, direct chat person. Yes. All right. So one person is right. I'm going to, does anybody else want to try anything in the, and he or she should submit for points, honestly. Oh, and there's another person in the direct chat. Okay, great. Yeah. Oh, we are 2 for 2. I'm so excited. See, we should be like this more often. All right, that is 2 people in the direct. And again, I hope you all understand. I'm not saying this to shame anybody who's not in the, but I'm also want to say that the 2 people in the direct chat now are different people from the ones who were in the direct chat before. And that also makes me super happy. Like, I feel like we're all together in the yellow submarine here. This is great. And my son is still asleep, so that's good too. Or he's got 14 video games inside the bed and is watching inappropriate YouTubes, which is fine too. Okay. So I'm going to use, yes. So here's what people are putting in the direct chat for the GDP now. The GDP is this. Oh, what? Oh, that's okay. Wait. Oh, maybe I shouldn't call attention. It was meant to be a direct chat, but okay. Yes. Okay, that's awesome. Got it. Oh my God. I can't even, do you know, oh my God, my 8-year-old is so into that Gotham thing and the wrong parts of it. I cannot, sorry. Yeah. Okay, but what Alex put in the public chat is what people put in the direct chat. This is awesome. That's 3 people. That's a hat trick. Okay. And I'm going to do it. Okay, I got comments. So first of all, well, okay. Okay, this is how I would write if I were taking this exam. First I would write, here's an example of the GDP is if in general, right? If Z is any general variable and that differential equation applies, then the solution to that differential equation is Z naught cosine omega t plus phi. Like, I'm going to explain this more in a second. But, and you might even want to say, if you were putting this as a GDP, like assume Z is any dependent variable. I know I'm writing that really small. Or, assume Z is any generalized measurable or whatever. But assume Z is some general thing. Then if D2Z, D blah, 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 if that differential equation applies to Z, then the solution to that differential equation is a cosinusoidal solution, right? And I'm going to note right now too, now that we're more advanced, since we did what we did last week, I'm saying that even the more general solution, I'm not correcting the people in the direct chat put like cosine omega t. And if you put that in the test, I would not take off point. Like, that's what we've been saying for weeks. Now I want to say, you could be even a little bit more general. We now know there could be a phi in that parentheses. Like, that's even the more general solution. phi could equal 0 as it has for weeks, but the true general thing would include a phi now. So that would be, I hope I'm making sense. You can ask in the direct chat if I'm not. But so you write this down, right? And then, so that's our GDP. Again, notice that's a general statement of truth. Like, I might not even know what that has to do with this yet. I don't even see any Z's in the problem yet, but this is a general statement of truth. So I can't, if you write it down, I'm not going to take off points. I mean, it's right, and it's certainly topical. But now, how is this going to, I'm going to add one sentence of English, that basically the thing that Alex said in the public chat. Thus, Z would oscillate harmonically at an angular frequency which is the square root of the proportionality constant in okay, what I'm doing here, I'm just putting in my words what Alex said in the chat, right? I'm now putting in English, in effect, what the purpose of this GDP is. It's saying in general, and this is still, I mean, this is one of those things, once you get it, it's like so simple once you get it, that it's like tiresome to keep hearing me talk about it. But until you get it, it like makes no sense. And I know that, so I'm going to say it again. Like, the point is, if we have a differential equation of that form, where the second derivative is equal to a negative sign times a constant times the original variable, then that constant we call omega squared. Again, I'm saying, and I'm saying here in the exam, in my words, that omega squared, the whole package, is just a name for that constant, whatever it is. We call it omega squared because we're saying that we realize that there's going to be a cosine solution, there's going to be harmonic oscillation, and the rate of it will be the square root of whatever that constant is. So we call that constant the square of angular frequency, right? So I've just written down the general statement, and I've written it now in English. Everything I've said here has still not solved this problem, right? It's all just truth about harmonic oscillation and differential equations in general. And I've on purpose written it in equation form and then in English. I'm going to tell you right here too, this is a good example. This is where, honestly, you really show your stuff on the exam. Like here, because yes, I'm telling you the answer and all that, but do you notice even, well, I can't, the way the people put in the direct chat was correct. They put the equations with the Z's that I just wrote. And then what Alex put in the chat was also correct. And he put it like in English. And then what I just put here was, first of all, was both. But second of all, my English was totally different from Alex's English. Alex would get full credit, so would I. But to be super honest, what I'm really telling you is the people that will really like grab my attention and rock this exam and really set up will be people that really go to the extra pains of using their words here. Like, this is where you want to use your personal language, or maybe even draw another picture if you want, or use highlighting or colors or whatever. Like, this is where you really show me that you really get what's going on. When you put it, the more you could put these things in your words and your pictures, the more I get that you get it. And the more you take risks to do that. And that's what you're trying to show me. Remember, I know that you know that I know that I'm telling you the answers to this thing. So you don't perform well by just giving me the answers back. I know they came from me. You perform well by proving to me that the actual solution methods have filtered through your personal brain. And you show that by taking risks of making it as personal as possible. Especially those of you who, and there are many of you who really take pride in your own notes, and you use different colors in your notes and you highlight things and that. Treat this exam that way. Make it yours and and even if you show where if you go right to the threshold of your own understanding, like when you start writing things that you're not even sure about, you can always write, I'm not even sure about this. But don't be safe, be personal. If that sounds weird, but if you know what I'm saying. And again, I'll move on in a second, but really step 3 and step 4, the GDP and the PAW is really your opportunity to really show that you get what's going on. The more, I promise you that all your answers will be the same, but your exams will, the more different your exams are, the more better grade each one will get, if that makes sense. Okay, I'll go on. But all right, so this is my GDP, and it's all to justify why now, and I think there's nobody in the chat, I think. So, but that's all the deal. So now I go to step 4, right? And I know that I'm going, the way I transition to step 4 generally is I'll write something like the word here, right? Or like in this case, or in this problem, right? I'm writing here. So now I'm zooming down to the specific situation here. Right here, the variable that we're talking about is theta, right? And I could have written z equals theta or something, but I'm saying now here we're talking about theta. So here, oh, so this is step 4 I'm doing now. I'm applying to the problem. So last side note, sorry. Also, I just said that for any D2Z, blah, 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 the solution is blah, blah, blah. And again, thank you, direct chat people who put that. Major points. When you go to do this yourself, you might even ask yourself the question, wait, do I have to show why that's true? In fact, I think one of you in the office once asked me that. Like, when I say that blah, blah equals cosine is the solution to D2Z, like, how do we know that? We know that because we take 2 derivatives and check it. Should you show that? Well, to be super honest, somewhere in this exam, you should. Yes. I'm not necessarily doing it now because this is problem number 2. And I think maybe the more appropriate place to show that is problem 1. But somewhere in the exam, you should actually take the extra 2 or 3 steps to show why it is we know that if d2z dt squared equals negative omega squared, then z equals z naught cosine blah, blah. We show that by taking 2 derivatives. It would very much behoove you to show that. Not every single time, but at least once in the exam. And again, if you show it, it's true, right? It's true. So it can't hurt. You can't lose points by taking that risk of showing it. So the more you can break your understanding down, the better. Again, bottom line, for the moment, I'll go back. The litmus test, as far as what to show me and how much work to write out, the litmus test is if anytime you're looking at your work and then you say to yourself, wait, should I show this step? The answer is yes. If you can think of a new step that you just did in your brain, if you can think of a step, even if it's I multiplied both sides by 2, if it even occurs to you to ask, does he need me to show that I multiplied both sides by 2? Yes. Because if you can visualize it in your brain as a step, then it is worth writing down as a step. The more you break this down into tiny steps, the better you will do. And also that means the more you'll believe your own work. The smaller the step, the harder it is to argue, which means the more valid the whole thing holds together. All right, anyway, any hoodles. So here, now I forget the equation. Right. Oh, and I need. So this is about 0.5. I think it's 0.5. Wait, we never did pi day. I'm so sorry. One day I'll. Actually, is this right? No. Is that right? Wait, something doesn't seem right about that. Yeah, I think that's right. Correct me if I'm. Actually, I would love it in the chat if anybody, that doesn't sound familiar, but if someone corrects me in the chat, that would be great, or confirms. But I believe, oh, good. Oh, thank you, bro. He's all over this. You see, you guys, you're always talking about Brian behind his back, but he's really cool. No, I'm just kidding. No one's talking about behind. Okay. Oh, but I got an actual smile from Tobias. Okay, awesome. All right, that's points, Tobias, for you right there. Okay, so I think that okay, yeah, well, no, and again, I really should be careful with these jokes, especially on Zoom. We need a whole Bitmoji board just for Zoom, just to make it clear that but anyway, all right, I think that's the answer. Approximately 0.524 radians per second. Again, I did 3 significant digits, partly because the problem asked for, partly because I think that's reasonable, because the original numbers that were given were to no more than 3 significant digits. But again, really the point when it said 3 significant digits, it was just to make it clear that I was going to get a number. All right, so that all of that, it was a lot of talking. If you think this is obvious, and it means you're good, because you can already see that this is like 2 of the big 3 problems on the exam were just like the same stupid method of just taking the square root of the proportionality constant. But we're trying to drill in that this method works for pendulums, masses on springs, temperature systems, subatomic particles. Like, this is harmonic oscillation across the universe. So there's angular frequency. Okay, that's that. So now switching screens again. Okay, now 3 is a little bit of a 3, same diagram. Okay, I've already said same diagram. I already said it, but whatever. So then 2. And I'm just going to remind you again, too, do you have to write step 1, step 2? No, you don't. But also just please remember that part of the other purpose of this whole 5-step method is it's a grading rubric. Like, that's it. So the more you write down step 1, step 2, you're basically just giving yourself a checklist that you've done everything to get the points from me. And if I look at a problem and I see step 1, step 2, step 3, it's just so much more likely that I can't take off points. I mean, really, you're just making it easier for me to give you full credit the faster I go. Whatever, you get it. Step 2. So what is the question? Oh, the question is for this was how many cycles per second, right? So really, this is asking for standard frequency, right? Well, yeah, it's asking for standard frequency, cycles per second, which is the same thing as a hertz. I keep losing cycles per second. Okay. So step 3. Okay, I think the GDP here is basically this. Well, okay, I'll be even more specific. I'd say a great GDP that you could always, one thing that never hurts, no pun intended, one thing that anywhere you write that down, I think you're doing yourself and me a huge favor. There's more than one ways to write it, but I think the principle here is that there's 2 pi radians to a cycle. I mean, to a circle, but to a cycle. A cycle is 2 pi radians. right? Therefore, and that is a GDP. Like that's I mean, that's about as fundamental as it gets for all of this. I mean, or okay, another way you could write it is you could write it like this. Like the definition of an angle is arc length over radius for a full circle. Pi equals 2 pi r over, over r. Right, that's where that comes from. Just to remind you, like, would it hurt to write all that? No, I would be thrilled if you drew a picture of a circle and showed that, and showed, oh, like angle mean, like we did on the board like 3 weeks ago. If you showed an angle as a section of a circle, and then you showed that for a full circle, the full angle is 2 pi r, the circumference divided by r, and you do great. And another piece of advice. Let's say you think that's stupid. You think this is so obvious, right? Maybe, and hopefully you do, maybe some of you. Maybe you think it's really obvious that a cycle is 2 pi radians, but you think it's obvious because you really get it, right? Like you really get it. You really see it in your mind. What students, including me, tend to do is the more obvious you think something is, the less you think it's worth discussing. That is the opposite of physics. If this is one little thing in all this that you really get, and a lot of the other stuff is a blur, but you really get that one cycle is 2 pi radians, I would highly suggest that you go to town on this bit of understanding. Like, give me a diagram of a unit circle. Break it down. If that one lecture was the one lecture that, and I'm not being sarcastic, if my one lecture on angles and how radians work made sense to you, then go to town on that part of the exam. Give me a lot on that. And that will give you a big cushion. Then in other places on the exam, if you're a little bit thinner in your understanding and a little thinner in your presentation, you've given me something great to work with here. It'll make me look at the rest of the exam more favorably, honestly. And also, again, I'm telling you all, I don't grade you from your middle. I grade you from your best. So wherever you see an opportunity to really explain something and really show that you really get it, do not think that you are wasting your time or mine. And it's like showing video in a class when you know you're going to turn off the video 20 minutes later. Don't think that if you go to town on this part here, that then you're setting yourself up for bad, because then when you don't go to town on some other problem later in the exam, it's just going to make it that much more clear that you don't understand the other problem. It might. But so what? You still didn't understand the other problem. The alternative is being thin on both of these problems and giving me less to work with. Don't do that. So go crazy here if you want to add a lot of extra to this GDP. Okay. Okay. We all get what I'm saying. So, but one cycle equals 2 pi radians. Why am I saying all this? Because for that reason, that's why the number of cycles per second equals the number of radians per second divided by 2 pi. Right? That's why that follows. Like, that's why that's a GDP. You could even say, I'm going to go to the next page. I'm just writing it again, but F in cycles per second equals omega in radians per second over 2 pi radians per cycle, right? And the radians cancel. and it's 1 over seconds, 1 over second, right? So, okay, I'm going crazy again, but I'm just trying to. Right. And you see the habit here, like whenever I'm in square brackets, that means I'm talking about the units. So I'm just showing you something about the units here when I go in the square brackets like that. But right. So frequency is in cycles per second. I mean, frequency is therefore omega divided by 2 pi. So that's all GDP. Everything I just wrote there is true, regardless of the particular details of this problem. So that was all GDP. And I went to town. Now I'm going step 4 PAW. So I say here, right here, omega is approximately 0.573 radians per second. Well, yeah. So F equals point. Oh, that's weird. Okay. Oh no, sorry, 0.523. I'm sorry. Oh yeah, I bet you were. No, I believe you actually, and that still counts as constructive participation. Not that no, I appreciate. All right, so we get now. So I think this. Oh, so that's step 5. That's the answer. A couple quick comments about that. I know I'm dragging this out. Like, I think that's the answer to that. And yes, I could be yes, I know for some of you, these are just exercises and maybe not worth all this discussion. Maybe. Say, right. Okay. So I apologize, but only sort of. I want you to notice one thing about, if you step back, if I weren't talking so much, if you step back, part of what this problem is trying to do is just show you how we get from that differential equation, which is like very abstract mathematics looking, to a cosine thing, to an omega thing, now down to a frequency thing. Like, we're trying to say, like, the whole reason for the radians, for the angular frequency conversion, all that is that the radians are what the math spits out. But as long as we always remember that there's 2 pi radians to every cycle, then what the math spits out gets us eventually to something that is physically meaningful and intuitive. We're saying that just looking at that differential equation, tells me that this pendulum is swinging back and forth, doing almost 1 cycle or almost 1/10 of a cycle every second, right? Which I don't remember if the problem asked or not, but if I now flip that, I can say, okay, I mean, it's doing almost 1/10 of a cycle every second. So it's taking a little bit more than 10 seconds to go back and forth. Like, that's that's a physical thing. I've got a pendulum that's however 5 meters long or 3 meters long, I can't remember. And it's going back and forth, like taking a little more than 10 seconds to do every cycle. I got that from working through the differential equation. I want you to notice, like, sometimes part of also this conversion is to remind you that pi is just a number. Like, I didn't get to do my whole pi speech on Pi Day, and I again apologize to Brian and everybody for that. No joke. But one thing about pi is, yes, it's a very interesting number, but it is just a number. It's just a number that's a little bit bigger than 3. Like, the interesting part is, like, how much bigger than 3 is it? But it's just a number that's bigger than 3. And so what I want to say is, don't think that radians always have to have pi's in them. There's a such thing as 1 radian. 1 radian is about 57 degrees. There's a such thing as 2 radians. There's also a such thing as pi radians. Pi radians is exactly a half of a cycle, or half of a circle, a half of a cycle. 3 radians is not exactly half of a cycle. It's a little bit less than half of a cycle. That's true. But you can have any number of radians, just like you can have any number of inches or feet or centimeters. I just want to warn you again, radians are just new and complicated enough to some people, and pi is just mysterious enough and Greek enough looking that what ends up happening to people is they sort of lump the 2 confusions together into one big confusion. We're trying to separate out confusion into little steps here. So pi is just, so when we said here, notice this angular frequency originally was written as pi over 6 radians per second. But that's exact. Pi over 6 radians per second was the angular frequency. That is exact. That's the advantage, is that it's exactly true. The disadvantage is it doesn't mean anything to any of our physical brains. Not mine either. Pi over 6 doesn't sound like anything I can find in a lab, and it's not. I can't measure pi over 6 in a lab. But then when I break it down, I realize, oh, what that means, pi over 6 radians per second, is that the thing is going about a half a radian per second. And what that, it's going back and forth about a half a radian per second. And what that really means is it's doing about 1/10 of a cycle per second, which means it's taking about a little bit more than 10 seconds to do a cycle. That we're trying to get you to see how physical the math actually is. This class is very mathematical, but it is a physics class. We're trying to show you that the math comes alive in the physical world, for whatever it's worth. Okay, but therefore, your job at the beginning and the end of every exam problem or every problem is to start with something physical, like a picture, and end with something physically meaningful, like a number of cycles per second. Like, that's the idea. The math is the vehicle, but it's not the landing spot. Last point, and then I'll move on. For those of you who have been paying attention in class, which is like everybody, I'm looking, God, every single one of you who's here right now is like, can I just point out that every single person here right now, even the people that are not talking right now or seem like they don't talk a lot, I just want to say that every single person here has at least once reached out to me directly, like by texting or something like that. Like, I feel like I know something about each one of you, and that's really great. And I thank you for that. Like, I know that, like, some of you reach out, like, whatever, just to say. So anyway, wait, so something just said something in the chat. Hold on. Sorry, I messed up. Oh, wait. Oh, did I write? Oh, sorry. Yeah, I did. Oh, yeah. Oh, thank you. I did. Wait, thank you, Felicia and Brian. Oh, that's multiplayer co-op. That's multiplayer. Okay, wait, sorry. Yeah, I caught that error, but I didn't catch it everywhere. Sorry. Yes, where it says omega equals 0.573, I mean 523. Thank you, Felicia, and thank you, Brian, for being. He said I messed up. Wait, I made an error. I have to. No, yeah, right. Right. Oh. Wait, was it 5? Wait, that's a good question too. Oh, I'm sorry. Wait, okay. No, you're right about that. All right, hold on. This is actually, again, not to get. So I made a mistake. I made a mistake. Hold on, God, are you? No, yeah, I shouldn't take the name in vain. Electron, I made a mistake. When I wrote 7, that was totally just a typo. But then you are right also that I shifted from 5.23. I shifted from 5.24 to 5.23. Let's talk about that for a second. So maybe even hold on. That's I think, and why does my calculator keep disappearing? Sorry. Not that I need a calculator. It's all just tattooed on the inside of my eyelids, I promise you. But hold on. I do want to respond to the Felicia thing. Totally worth. Well, yes, also that's true. But hold on one. Okay. A quick thing. No, first of all, I'm just glad that Felicia and everybody is paying close, and Brian and everybody are paying close attention. Totally worth pointing that out. Yes, I just made a typo at first, but as far as 0.523 versus 0.524, here's my honest thing. Oh, is there a big difference between the two? No. And like, if you were writing one, but I thought it was the other, you wouldn't lose points or anything. Like, this is not at a certain point in a lab, that can make a difference. But no, like, I wouldn't care about the difference between 0.523 or 0.524. But just like it was if I'm trying to teach a class here, it's certainly confusing to you guys. If I write 0.523 on one page, and then I write 0.524 on the next page, you don't know if like it makes you confused because I might have done that. I might be making some point that you don't understand, right? Like you don't know if I'm doing some physics procedure that you missed or if I'm just being an idiot, right? Which is why it's like totally worth pointing out because you need to know what am I trying to convey something with this 3 to 4 shift or am I just making a typo? Which is why it's like totally worthwhile that Felicia and Brian pointed that out. So same thing in your test. In your test, it's just like the diagram. The whole thing is about self-consistency. It's not about perfection. Perfection's impossible. But we do want to strive for self-consistency. So you can make your free body diagram any direction you want, but you really want to make it consistent with your original picture. Same thing with me here and you there. Like, I'm not going to die on the hill of 0.524 or 0.523, but you do, I want to be consistent. And so I do need to apologize for this. And now I'm going to defend myself too. Like this is a rough draft you're seeing, right? I'm doing this spontaneously in front of you for good or for bad. That doesn't excuse my errors, but with your exam, one of the reasons we're doing a practice now is this is the rough draft for all of us. This is the rough draft for you to practice for your actual exam. And the practice exam is a rough draft for me to see, to make sure there's as few errors in the exam as possible. Like, honestly, so by the time you turn in your exam to me, you do want it to be a final copy that you have checked for things like that. I'm not trying to turn the thing back to you, but I am. Like this is our opportunity to make mistakes and catch them on the final. I better hope that I have as few errors as possible when I present you the exam. And you want to have, again, remember, I know that you know that I know that I gave you the answers to a lot of it. So your job is to make it as beautiful and polished and corrected as possible. So it is worthwhile that Felicia pointed out that 3 to 4 shift was a mistake that should be corrected. Okay, sorry. Wait, no, but it is. Wait. Okay, now Felicia. Okay, wait. And Felicia's still fair, but I feel like that literal thing that Felicia just said about being consistent. And no, I'm all for it. I'm all for it, but I thought I literally just checked that on the calculator. I thought I agree with her that whoa, that's a cool, talk about a Bitmoji. Wait, hold on. No, she's right to say that. And Alicia is right but I thought I just checked that. The funny thing is, I thought I just checked that. And I have a feeling I know why we might be both. And you know why though? Why this is worth, we're going to move on in a minute. Like, obviously we have to, no, okay. You're not crazy. Look, if you're crazy, then you're in the right place. But, I see why you, okay. Yeah, you're not crazy, but I think, hold on, my computer's going crazy. This just brings up one. Oh yeah, Brian's definitely crazy, no question. No. Oh, okay, fine. And I will move on. And I appreciate everybody's honesty and self-reflection, all that. And again, all of this, I'm so defensive. I know I'm such a used car salesman, but all of this chitter chatter between us, if any of you is ever thinking like, can you get back to the topic, please? Yes, I will. But I will also just remind you that the more there's chitter chatter amongst us, in the longer run, the more we are all engaged in this material. Like, I'm for it. I will get back, but it's worth it. It is. Bottom line, you go to a party, you introduce yourself to people like, hi, I'm Alicia. Oh, hi, I'm Dan, whatever. And you ever notice that you do that? You're like, hi, if you're Alicia, whatever. Like, Alicia's like, hi, I'm Alicia. Hi, I'm Dan. And then 3 minutes later, you're like, wait, didn't I just introduce, like, how come we just introduced ourselves and I can already not remember that crazy person's name? Like, what's my problem, right? Doesn't that always happen? And you know why? Even right after you introduce yourself to someone, you can't remember their name? Because of exactly the way I just phrased it. Because it's 5 minutes after you introduced yourself to someone. Because when we introduce ourselves to people, what we're actually, we think we're finding out their name. We're totally paying all of our attention to how we say our own name. We're far more concerned about what we're saying to the other person than what the heck they're saying to us. Am I right? Like before the party, you're really worried about what you're wearing and what other people are going to think about it. It doesn't occur to you to go to the party and judge. I mean, maybe you do a little bit, but you're generally much more concerned about what you're wearing. And you're generally spending a lot less time thinking about what other people are wearing than what you think they're thinking about what you're wearing. Maybe it's a dumb example. Maybe not everybody's about clothes. Clearly I'm not. But where I'm going with this whole dumb analogy is we think when we talk. We don't think when we listen to other people talking, right? And that's why I get the advantage of understanding. I get to talk all the time. So I'm always awake and I'm always hearing what I'm saying. But the more you guys talk, even if it's these jokes and stuff, the more you're actually hearing what's going on. Therefore, okay, you get my point. And meanwhile, my computer is going crazy and like trying to get me to sign up for things while I'm trying to teach. Stop, computer. Okay. Okay. All right. But the other thing is, even though Alicia's apologizing, one thing that might be happening too is when I just divided on the calculator, just for the record, I divided by 0.628, which is my rounding of 2 pi. You might divide on your calculator by 2 pi, and that's fine too. But just to warn, and it's a little bit more exact because your calculator will have a few more digits than 3. But it's not, just please understand when you press that pi button on your calculator, you're getting more digits, but you're not getting infinite digits. So don't think that that's perfect either. You're perfectly welcome to chop off the digits and call it 6.28. But big warning, because this happened in another class to a lot of people and it really messed them up in lab. If on your calculator, you ever want to divide by 2 pi on your calculator, you have to be sure to either put parentheses around that 2 pi, depending on how expensive your calculator is, or divide by 2, get the answer, and then divide by pi. If you just divide by 2 pi, it's actually going to give you the wrong answer because of order of operations. So for a minute, actually, what I thought was going on between Felicia and me, I thought maybe one of us was using pi on the calculator and one of us was using point, which is possible too. And so I'm flexible about all these digits. But yes, consistency is the standard. Okay. Oh, is that what's happening? Wait. Oh, okay. So that's fine. So I'm just looking at, okay, I'm looking at all the chat. Okay. But so I have to be flexible about the numbers, but what you're trying to do, just like what I'm trying to do in class here, you're trying to give me as much to work with and as little room for confusion as possible. So yeah, if nothing else, what this is all a plea for is, please, with your exam, do one rough copy and then do a final copy. We all know you're not doing it under time conditions. We all know you can use all the resources in the world. You know that I know that. So treat it that way. Treat it like you've gotten all the advantages. So now the idea is to make it as pretty and clear and readable as possible. It is about presentation. I'm ashamed of my boards. They're disgusting. But part of my excuse is I'm sort of trying to make up for lost time and move in real time and not, and the alternative is a PowerPoint presentation that's pre-made and will put us all to sleep. But that is partly an excuse. My boards should be much better than they are. And the burden's on you to, if you're thinking you hate my boards, good, turn it into love and show me the better way. Be a parent and role model for me. Okay. Okay. Well, thank you. See, I just totally just like fished for a comp. Thank you. No, I totally appreciate. Okay. No, I totally appreciate that, Felicia. I'm going to move on now. Thank you. I hope so. That is the judgment call I'm making, but they still could be. All right. So I'm going to go. All right. So that's the last thing about this answer. A cycle per second is a hertz. A cycle per second is a hertz. So I do want to say that you could perhaps go an extra step and say something like 1 hertz equals 1 cycle per second. Therefore, F equals 0.083 hertz. But the reason I'm not doing that, and the reason I'd be careful about that if I were you, like if that's something you want to show that you really get what's going on, please do. But do notice the question didn't ask for hertz for whatever reason. I don't even remember why, but the question asked for cycles per second. So I'm boxing an answer that answers the question. If I want to go a little farther and then make a comment, fantastic. That will just make, if I'm you, that will just make me love you more. But I have to answer the question the way it's asked. And so there it is in the box, cycles per second. Okay, that, and Alejandro has come back. Okay. Okay. Oh, wait, Alex is smiling. Okay, I'm gonna go. I'm going on. If we ever get through anything, it'll be a miracle. All right, I'm going board. Oh, now 4. Now this is hard, actually. I mean, this is like no joke, this question. So 4, C diagram. So what is the question? Oh, okay. So the question is, oh, sorry. Okay. Okay. Now this is no joke of a question here. This requires some thought and some serious GDPs. And I'm going to warn you, as another reward for paying attention right now, this one, I'm going to say a bunch of stuff about. This is an example where it's very likely that I will ask this in your actual exam, but where it says at t equals t over 4, that's going to be subtly changed in your exam. I mean, subtly, but watch out for a change there to make, I don't know what the change will be, and I'm not guaranteeing it, but it's very likely that I would change. Like, this is one that I'm going to want to make sure that you understand the concept and you apply it to a different number. So, okay. So what it's asking, so my first GDP here, is it capital T? Oh, okay, it says it, but still, capital T is the period of pendulum, and period stands for the amount of time for one full cycle, and it's measured in seconds, right? That's a GDP right there. Because otherwise, it's a very confusing question. It is confusing to a lot of people, like T equals T over 4. Like, what? How does T equal T over 4? What it's saying is that the time equals 1/4 of a period, right? It's asking, what is the speed at 1/4 of the way into its cycle, right? So there's a couple of, so it's true that what a lot of people will do is jump straight to what, like, okay, I could even write this as a GDP. Like, say I'm taking the exam right now and say I don't quite know how to do this question yet. And I think that's possible. Like, you might, hopefully you understand what it's asking. It's asking how fast is it going at a certain moment in its journey. Oh, you know what? I'm even going to add another GDP right here before I go any further. Okay. I'm sort of pretending that I'm taking an exam right now. In that, I'm looking at this question, and I'm not really sure yet how I'm ultimately going to answer it. Like, I don't see the end of the tunnel here yet. So I'm already getting a little bit nervous. Like, I think I get the words, like, okay, speed. You know, I don't think it's a crazily complicated sounding question, but it doesn't sound like a question I've prepared for just yet. It's asking for speed at a certain time. So the first thing I'm writing down, I'm reminding myself that if it's asking for speed at a time, that means just that, speed at a time. It's asking for instantaneous speed, and I'm writing down here as a GDP that speed is not the same, that instantaneous speed is not the same as average speed. Now, this is do all of you have to write that to get full credit? No. A lot of you might not write that, and that's fine. But it's a word of advice. Oh, wait. Oh, sorry. There's something in the chat I missed. Okay. This is where I'm trying to give you test taking advice, because I think this question, we're going to do it, and it's like not a short question. I don't know if you see how to answer it already or not. And I don't know if I'm going to lose. Hopefully I won't lose you in the middle of my explanation. But what again, I'm trying to prepare for you is not just like the material, but I'm trying to train you in what you do when you don't know what to do, right? And so like, I'm starting to answer this question. I'm a little nervous because I don't know if I know how to answer it yet. And what I'm trying to do with GDP in part is diagnose my own nervousness or my own confusion as I go in order to turn the confusion into a solution. In other words, what I'm saying is I look at this problem. Now, what a lot of people in past years did when we didn't practice or whatever, they got this problem, it asked for speed, and then they started writing down for GDP or whatever, they would start writing things down like speed equals distance over time. Okay. And like the average speed equals distance over time. That's true. And if you literally write average speed equals distance over time right here, if you write V with a bar over it equals distance over time, I would not take off points, because that is true. That is a true statement. But then if you start using that to solve the problem in step 4, we're going to be in trouble, because this problem is not asking for average speed. That you can't take a distance and divide it over time. Or also some people in the past would write like speed is distance over time, and then they get really stressed out because they couldn't figure out what distance to use. And so then they would like panic and freeze. What I'm trying to say is, okay, actually the issue here is we're not asking for average speed. We're asking for instantaneous speed. And honestly, if you're anything like me, or if you're ever nervous at all, that might be the part that half consciously starts panicking you. If you start being like, wait, I don't know how to solve for, wait, this is instantaneous speed. Do I know how to solve for instantaneous speed? I don't know. Or even if you think, what I'm saying is, try to notice the minute you start getting nervous in your mind about what's making the question hard, whatever seems to be making the question hard, you should write that down as a GDP, even if it's a statement of something that you think is fault, like what's I'm writing down. Instantaneous speed is not the same as average speed. That's actually my problem. Like maybe I even wish it were, because then I could solve the problem easily. So what if that's my issue? That's probably the issue of the problem. So writing it down will help me. So the more you want to write in GDPs about your observation about what's going on, even if it's your observation about what you think is going to get you into trouble, write it down, because you will get into less trouble for doing so. I'll say this one last way, but again, this is 30 years of frustration speaking, or trying to help you, is a mistake we all make as scientists, as young scientists, is we're so interested in getting things right, and we're so used to getting things right quickly because we're smart, because that's why we're here, that we get really scared when we don't see things right away and we freeze. What I'm trying to tell you is the great habit to develop is to be able to move forward even when you don't see the destination. As long as you just keep moving forward, you'll land at the destination. But get rid of this idea that you have to see the destination in order to move forward. We want to get rid of that idea as scientists, and it's hard to get rid of. So I'm just writing a bunch of crap down. I'm writing down, okay, now what I might do, what you might be tempted to do is start plugging in numbers. You might start saying, well, okay, okay, well, I'll even say, I'm still in GDP land here. I might even do this. I might say T by definition is 1 over F. That's also a GDP, right? And what I might be starting to think is that I can use my F from the part above and flip it to get a period. And then I could divide the period by 4 to get the time. I could do that. Okay. Hang on one second. I could do that. And if I'm going to start plugging in numbers, then I think that means it's time for PAW for step 4. Now I'm going to tell you right now, that's not what I'm going to do. It's not what I'm going to do right here. But I'm also going to tell you that if you do that, fine. It's all correct. If you take the period from the top part and you flip it, I'm sorry. If you take the frequency from the last part and you flip it to get, okay, I'll even write in parentheses. It's really weird that my calculator keeps disappearing. Sorry. Hold on. Oh, yeah. Okay, so I'm making a compromise here. I'm writing down that Sorry. Okay, I'm writing that down because honestly, a lot of you that might be the first thing that occurs to you if you were taking an exam, especially if it were in real time and all that. That might occur to you to do, and it's not at all crazy to do. It's very logical and it's very true. So, I mean, and technically, I think it's like step 4, not step 3, but you'll see why I still feel like I'm in step 3 in a moment. Oh, crap, my dog. We might have to take a break in it. Yeah, we will take a break in a couple minutes. But if you do this, what I really want to say is I'm now going to solve the problem without that information. I don't actually think that's the information that's going to land me the answer. But so what? It's still true. If that's how you're thinking, I mean, even though you're going to do a rough draft and then a final copy, if that's true information as part of your thought process, write it down. And then if you go in a different direction, okay, you can even like put parentheses around it like I just did, but it's part of the thought process. Again, just because you end up doing something that you don't end up thinking is the thing, don't like sit there and erase everything you did and then start beating yourself with a whip and being like, oh my God, that was totally wrong. I'm the biggest loser ever. Yabberbaum's the biggest ass girl of questions ever. Like, right? This is still logical physics. It's valid. But however, I think the way to go about the problem is this. And when we finish this one, we will take a break because the dog is barking, which is probably a way of saying the sun is awake and blah, blah, blah. Oh, sorry. That's not what I meant. Sorry. That's not what I meant to do. What I mean to say is this. What I want to say is that T/4 was not a coincidental thing to pick as the value here. I mean, some things are coincidences, but it's always good to take questions seriously. Always assume that questions are written in the way that they're written for a reason. I mean, that assumption doesn't always turn out to be correct, but it's always a helpful assumption to start with. T/4 is a quarter cycle. So what we're at, right? So a full cycle is, and the cycle begins at the amplitude position. It begins at at the amplitude position. So a full cycle is from positive amplitude to negative amplitude back to positive amplitude. That's a full cycle. That's 2 pi radians. A half cycle is from positive amplitude to negative amplitude, right? Just there, but not back. So a quarter cycle is from amplitude to equilibrium. And this is always true regardless of whether we're talking about a pendulum or a mass on a spring or whatever. And it's true regardless of how far in space a cycle is or how long in time a cycle is. This is why we like talking about cycles, because there's things about cycles that we just know that are universal about cycles. And we know them mathematically through all the cosine and sine facts about circles. So what this problem is really asking is, how fast is this thing going when it's at equilibrium? That's a special point that we have knowledge about. On your test, on your actual exam, will I necessarily ask how fast it's going to equilibrium? Maybe not. Maybe I'll ask like how fast it's going at the other amplitude point, or maybe I'll do some other special thing. I don't know. But you want to look out for the fact that we're really asking you to focus on knowledge of the cycle. So this question is, right, what this question is really asking is, when theta equals 0, what's V? Now that's possibly an easier question to answer than like a lot of arbitrary thetas I could think of. Right? I mean, it sounds like a question about time, but it's really a question about theta. Right? So I'm going to add another GDP then. Well, I know. Wait, hold on. Well, okay, I've got 2 options now. I'm going to do them both. I'm just thinking which is I'm looking at the time. Okay. Here's option 1. And when I say there's 2 options, what I honestly mean is you could do either one. I would recommend you do the one that you understand better and that you could do more thickly. If you really want to be a rock star, you could do both and show that they get the same answer. That would be amazing. But I'm going to show you. Option 1. Okay, the break might come at a weird moment because we might be about to be interrupted. I think I hear the pitter patter of Pokemon feet. But okay, so one thing, we spent a long time in homework 1 doing all this business about energy conservation and developing remember all these potential energy is the integral, work is the integral of force, and then the integral of force transfers energy, but then potential energy is the integral of the conservative for all that stuff. Well, there was a reason for all of it. It applies to any harmonic oscillator, including a pendulum on a string. Energy is conserved, which means, so this is all GDP that I'm doing here, right? the total mechanical energy at any two spots in this pendulum swing have to be the same. At theta equals 0, at theta equals theta dot, and at theta equals 0, they have to be the same. And what is total mechanical energy? It means the sum of all the kinetic and all the potential, or other way around, whatever. Right? This is all that's option 1. I'm going to move now. I'm going to start applying that to this particular problem. So I'm going to move to step 4, PAW, and I will give you option 2 as well. By the time we finish all of this, this might be the class, strangely. I'm just going to keep going until we're interrupted or until I finish this problem. But so okay, I'm going to warn you right now too, and please maybe put this in your notes. I'm starting to try to go a little bit faster because I am watching the time and all of that. So even this, I'm doing, I would say this gets deep. And this is another opportunity for you to really go to town. Like there's actually a lot to be explained here and a lot of variation for people to explain it different ways. And the more you explain this, the better. I'm giving you a pretty short version right here, to be honest. And I'm going in kind of a funny order. What I'm saying, like we're going to do energy conservation here, potential plus kinetic. Now, the potential, I don't just want to skip to a formula, and you don't either. One of the reasons we spent a long time on this stuff is to be able to universalize these concepts to any new situation. The potential energy. So I'm skipping steps here. I mean, really, I'm like, you may want to, I'll put in like one more just to be clear, but please put in your notes, like we need more steps for this. I'm giving you a bare bones solution, like potential energy. If you look, we did a whole lecture on this. Potential energy has to be the change in potential energy is the work done by the conservative force to bring something from a particular spot back to equilibrium, right? That's the GDP. Potential energy is the work done by a conservative force to bring something back to equilibrium. Now the conservative force doing work in this case, in the case of a pendulum, it's not the spring force. There's no spring. It's not Kx. It's gravity. How do I know that the conservative force doing work here is gravity? Because my free body diagram, like, and I would even say this, okay? I'm saying it, like, please put in your notes. Like, if you refer to the free body diagram, there's two forces acting on the pendulum, gravity and tension. They're both acting on the pendulum, but the tension in the string is always perpendicular to the displacement of the pendulum bob, to the motion of it, to the velocity of it, right? Whenever like the radius of a circle is always perpendicular to any tangent line to that circle at that point. So whenever the bob is going like this, the tension is going like that. Whenever the bob is going this way, the tension is pulling straight up. The tension is always perpendicular. And remember, we made this whole big thing about dot products. That work is the dot product of force with respect to displacement, that the work that a force does is only the component of that force that is parallel to the displacement. So, and you want to say this, like, because this is all, like, this is whatever, you want to say this. If you look at the free body diagram, there are two forces acting, but only one of them is ever acting parallel to the motion of the object. That one is gravity, not tension. So the work done by the conservative force is, so the conservative force that's doing the work is gravity. So we want the integral of gravity from one place to another to bring this object from one height to equilibrium. But remember, it's a dot product. You're only looking at the component of gravity that is parallel to the displacement. So gravity is always pulling down. Gravity, as your free body diagram indicates, gravity is always pulling down. So it's only being multiplied by the component of displacement, which is down. We only care about gravity is only doing work to pull the pendulum down or up. So we integrate from one height to another, right? In other words, what I'm going to say now, I hope you're with me. I know I'm looking at the time. So if I draw a diagram now this is all part of solving this problem. This is option one. Option two, you will either find easier or harder depending on your, but if I draw a diagram here, if I look back at the original diagram, right? This is theta naught. This is theta equals 0. I'm integrating. I'm trying to figure out the work done from here to here. That's H, right? The height drop from only the height drop, only the vertical component of displacement matters, because only the component of displacement that is parallel to the force matters for work, right? Dot product. So H, that's what I'm looking at, that vertical height H. In other words, I'm looking at this right here. That's H. Well, and would I include this diagram if I were you? Yes, I would, please. And if nothing else, use this diagram in your notes, in your practice, as a signal to remind you that this all needs to be explained. That's supposed to be the same H. It doesn't look like the same H, but that's the same H. Right, H. Now, how can I get, so I need to know what that H is. Wait, so, okay, so hold on. So potential energy, by potential energy, we mean gravitational potential energy. Gravitational potential energy equals the integral from that height H down to that height 0 the integral of mg dy, but mg is a constant. It comes out of the integral. I'm doing this sort of fast. You, again, think about it at home and review it. The parts you really understand, write a lot about. The parts you understand less, like learn, but write less about. So I have this. The integral of dy is just y. Sorry, this should be negative. I'm going to turn back the page in a second, but I'm just saying, what I'm trying to say is this. I'm trying to say gravitational potential energy equals mgh, which I know a lot of you knew from physics 1 or from 7th grade or something like that. Gravitational potential energy equals mgh, but because of all the reasoning that because of that integral that I just did sort of quickly, gravitational potential energy equals mgh. It's the force times the vertical component of displacement. But now, what is h? Like h was never given in this problem. H is that bit in that diagram. It's just the amount that it falls. How could I possibly know H? Well, I know it because if I look at this diagram, which is why this is a very important diagram, if I look at this diagram, that whole thing is L, right? Like the string cannot change its length as it's moving. When it's all the way, when the string is fully vertical, it's still a full string. Or put another way, all radii of a circle are congruent, right? It's L, whether it's pointing straight down or it's at an angle. So if that whole thing is L, I want that whole thing minus this bit here. That whole thing L minus this bit here will give me the H that I'm looking for. And from SOHCAHTOA, that bit there, I know I'm saying this fast, but that bit there is the adjacent side in a right triangle. It's adjacent to the angle theta. So it's hypotenuse times cosine of theta. That bit is L cosine theta. What I'm saying from this diagram then is that H, my conclusion is that H equals L minus L cosine theta. I'm rewriting H in terms of the knowns that were given. What were given were theta and L. So, long way of saying, well, so H is L minus L cosine theta, C diagram. Right? So, therefore, potential energy, gravitational potential energy equals mg L minus L cosine theta, or in other words, mgl1 minus cos. I just factored out an L, right? Oh, yes. Sorry. Wait, I hope I'm. Wait, thank you for asking. And that also indicates that something is. Yes, definitely. I'm just making sure the recording is actually happening. Yeah. Someone just asked if I'm totally posting this recording, but yes, thank you. Yes. And also, I'm going to give you the PDF for what it's worth. But yes, I'm going to take that to mean that. Yes. Oh, right. Right. It's totally, yeah. Well, there's that. Yes. Okay. And I'm going to try to make tracks here because I know, but tell me if I'm going, anyway, anyway. All right. So now then, thus, why am I in this wrong color? Thus, so kinetic energy plus potential energy over here must equal kinetic energy plus potential energy over there. I'm about to fill in what kinetic energy and potential energy mean. But now remembering also from like homework 1, at theta naught, that's when the whole problem just began, when the object was still. So there's no kinetic energy over there. And then when the object came down to theta equals 0, there was no potential energy down at the bottom, right? So what we're saying here is MGL1 minus cosine theta equals 1/2 mv squared, right? And the m's, I hope that makes sense. You can stop me if it doesn't. The m's cancel out. You can divide both sides by m's. And the v is what we're solving for. So v squared equals 2GL1 cosine theta. So v equals, that's an L. So v equals square root of 2GL1 cosine theta. So v equals approx. So this is all, I think we're all on step 4 here, right? We're still in step 4. Yeah. So this is all step 4. And notice I'm leaving the numbers for last. Good strategy, I think. So now v equals the square root of 2. Honestly, we should go like this. 2G L L is so now I don't remember the, hold on, let me just get to L. And cosine of pi over 12, that's, yeah. I'll go back in a second if that's. Okay. Okay. I want to move on, and I said you were going to have a break. And but since things are quiet, if I end up, instead of taking a break, if we end up going 10 minutes, 10 minutes early, that'd be fine too, I guess. I do want to finish this problem though. And it is kind of crazy that, well, yeah, I'll say quick things about the other problems, and I will post some things about the other problems too. This was a walkthrough, and I think this was the hardest problem to do. And the most different from anything you've seen. So I think it's the most useful. I will post some other things as well. But yeah, looking through the rest, I think, but anyway, let me finish this. So I think that's an answer. I'm going to show you the other way to do it in one moment. But I think that's an answer. As a technical point, you notice I'm leaving the G as G. If you changed it to 10, because of the nature of this problem, I would take off very few points. I might take off 1 point, but it wouldn't be a big deal if you changed it to 10 or 9.8. But the reason I'm not is because it has that warning at the beginning that we don't actually know what G is. And the reason for that, again, is so that we didn't just plug into square root of L over G at the beginning, or G over L at the beginning. So technically I have to leave G as G here. if that makes sense. But that is a technical point. That's not a huge deal. This is my answer. I mean, obviously, if it weren't for the G, then I could take the square root of 0.068 and get even a more numerical answer. But that's my number for that. That's how to do that. But there's option 2. I'm going to do somewhat fast. Option 2 is back to GDP. Sorry. Now you might recognize this from lab. What I'm writing here, just going back to option 2 is to realize, look, angle measured in radians is defined to be arc length, like as in meters, divided by radius measured in meters, right? And velocity, instantaneous velocity, is defined to be derivative of length. Oh, sorry. Right. Sorry. Wait. Hold on. There's a good thing in the direct. Okay. Velocity is dx dt, but x, length, position in space, meters, is theta times r, right? Just by definition of theta. So velocity is time derivative of x is dd, right? Velocity is d dt of x. So it's d dt of theta times r. R is a constant. It comes out of the derivative. So v equals r times d theta dt. Velocity at any moment is the derivative of angle at any moment times r. If I'm saying that fast, but and then you use this in lab like that's a while ago, but you might want to think about it, but it's true. So therefore, what I can do, step 4 PAW, right here is I can take my function for theta and differentiate it twice. Like this now goes back to what the 2 people in the direct chat said like an hour and a half ago. We said here, theta equals theta naught cosine omega t. Technically, I said plus phi, but phi equals 0. Okay, so like people put in the chat, they put this and they're correct. So if I take one derivative of that, right, I'll get this. If I take one derivative of that, I get this. And we're saying that V by definition equals R times that derivative. So it equals this. Right? So if you do understand derivatives and you understand this relationship of angle to arc length, maybe this is a lot shorter to do. Maybe, and it's totally valid. So now I'm going to plug in. So omega, and for this, I would probably leave things in terms of pi, at least as long as I can. So omega, we said omega equals pi over 6. R equals 3, I believe. So R equals 5. Oh, did I screw that up? I might have screwed it up on the last one. You tell me if I plugged in the wrong, but theta naught equals pi over 12. And then sine of pi over 6 times well, now you know. Now here's the thing. The sine oh yeah, okay. One second, I'm just looking at the time. Well, right. I'm leaving. So this time I'm just taking a little extra thought to leave everything in terms of pies because I think it'll be easier to look at the sign and all of that. So V equals negative. Pi squared. Sorry. Okay, I guess I shouldn't circle that because that's not my final answer, but okay. Okay. I'm obviously I'm kind of watching the clock here. I'm a little concerned. I really did want to give you a break, but I also don't want to. Okay. Oh, but ask for speed, so it doesn't matter. All right. Okay. So very quickly, here's my answer. Doing it this way, one way is easier if you understand calculus. The other way is whatever. It doesn't matter. If and I said you could check that they both equal each other, but you can only check that if you know what G is. So you can't even check that they're the same. But it asks for speed, so I got rid of the negatives. The negative sign is correct for velocity because we're calling the positive direction, whichever way the angle opened up. So the thing is moving down by the time it gets to equilibrium. So that's the negative direction. So that's not an error, but it asks for speed. So I got rid of the negative sign. I could leave it either form. I liked to leave everything in terms of pi until the last minute because it was each because I could see like the sign of pi over 2 is 1. It just made my life easier and a lot of more cancellations. But then at the last minute, I converted the pi so I could get a number I could relate to. That's a judgment call. Either way is fine. But that's the answer to that because it's 10:30. I'm going to quickly. It's 10:30. I want to back up for a second. I want to leave on a large scale note here. So the very last question of this part 5 is a little mini proof. And I think you did this in lab, honestly, like a long time ago. I'm going to sketch it out. I'm going to not talk. I'm just going to sketch it out for you so you see what I'm looking for here. I am watching the clock. It looks like I'm not going to be able to give you a 10-minute break. I'm sorry. I will let you, as soon as I do this and make my comments, I'll let you go, hopefully like 5 minutes early or something. You've been very good. I think it'd be worth it for all of us to end with closure here. So here's a sketch of what, first of all, you've got to make a component free body diagram to understand this last question. You've got to take your pure, I'm going to not talk. Okay, look, I'm scrolling this out so you get a sense and you can look, and of course I'm going to post this PDF. I'm saying quickly, if you draw the component free body diagram, you got 2 axes. The forces are not balanced on this axis. One minus the other creates the centripetal acceleration. It doesn't equal 0. It creates the centripetal acceleration. But that's that axis. That's not relevant to the axis of motion, which is the tangential axis. The thing moves along the tangent line. So if we then go to that axis, the F-net statement is negative mg sine theta equals ma along that axis. Okay, so I'm just writing mg sine theta equals ma. A is d2x dt squared. So we have mg sine, and x, we just used this a second ago, x equals r theta, right? So mg sine theta equals m d2 I'm just writing this. Almost done. I'm looking at the time. Okay. The radius of the circle is the length of the pendulum bob. Okay. So we have this statement. So going to the next page. I'm going to say this very quickly. This is a small angle pendulum. So if you're looking at the note to the side, to small angle pendulum in the for small angles, the measured in radians, the sine of the angle is approximately equal to the angle itself. Try that on a calculator. In a limit, when the angle is 0, the sine is 0, right? So the smaller the angle, the more you can just replace sine with theta itself. So we can say this. I know I'm saying this quickly. And therefore we can say this. And what we're trying to say, what this argument, if you use your free body diagram and break it into components and you acknowledge that the angle is small, so sine and theta are interchangeable, then you land at that differential equation, dt squared equals, I'm sorry, equals negative G over L theta. That shows, oh, this thing is a harmonic oscillator and the angular frequency is the square root of whatever is the constant. That is the proof that a small angle pendulum approximately is a simple harmonic oscillator, just like a mass on a spring. And the angular frequency is the square root of whatever that constant is. So that's the proof right there. I know I just did it very quickly, but that's what I'm looking for. I mean, you'd have to talk about it more and explain it, but that's the idea. Now, I know we have 3 minutes. I apologize for the lack of break. I will post more on the other problems. The very, very last problem has to do with the lab that you did, lab 3 and lab 4, and the thing that I just put on the board at the end of last class. I'll try to post some hints about that or whatever. Most of the rest of the test we really have talked about. Most of it, I mean, we've practiced in one way or another. Stuff about E, I'll try to post something about too, but I'll be aware, I'll know exactly what I went over here and what I didn't, and I'll take that into account when I post your actual exam. I think we set now, I know we've two, I'm looking at the chat. I'm looking at the chat. Oh, okay. Oh, thank you. Thank you. Okay. I appreciate it. That's very nice. Okay. Okay. I want to let you go. Yeah, we said I'm going to post this thing. You better remind. We said this thing is due back Tuesday morning before you have class, right? If you have any issues or anything like that, let me know and I'll comment it, but just let me know in advance. But I'm going to post it. I will try to post it by Thursday night, 8 p.m. I mean, yes. And you can text to remind me to do that or whatever, or text to remind me if what I'm saying right now is anything different from what I said to you last week. But I believe that was the arrangement, and I'll clarify it in Google Classroom. But I believe I'm posting this thing, the real thing, Thursday night of this week. You've got, I don't remember if I said Thursday night or Friday night, but you've got till Tuesday morning to do it. You can work together. You can help each other. You can go on the web, all that stuff. You can't really ask me questions about it once it's posted, but you can before, or you can ask me and I'll just decide whether I can answer them or not. But the point is for you to make as clean and beautiful and clear and thorough a copy as possible on separate sheets of paper. Make it so that I can grade it without looking at anything but it, if that makes sense, and make it as personal as possible. All right, I'll pause for a second. If there's any questions right now, you can text me or email me and all that. You've been very, very patient. You are a wonderful class. Sorry to keep you right to time. But thank you and have a great day.
Thank you, Professor.
Thank you. Have a great
Thank
day.
you.
Thank you.
Bye.
Bye. Have a great day. I will post all this. Have a great day. May the net force be with you.